Hello, my name is Richard Janke, and I'm Director of Engineering for Galixsys Networks. Galixsys Networks began in 2008 with conversations between my son and I. He's also an embedded hardware and software engineer with a BSEE from Northwestern and his master's degree from Rice. We were discussing a recent flurry of articles about how the internet will be used to connect all manner of commercial, industrial, and personal devices. During that conversation, we decided to pursue a project to find our way into this now infant industry. He was living in Dallas while I was in Los Angeles, so we each bought a BeagleBoard, which is a low-cost, network-enabled platform based on a Texas Instruments ARM Cortex processor that supported the Angstrom distribution of Linux. Our goal was to have one board send a command to the second board to blink its LED, and respond with a command to the first one, originating board, to blink its LED and restart the loop. Basically, to get the boards talking to each other without human intervention. What we quickly discovered was the text-based and stateless nature of the internet, while being very good at moving large files for human interaction, was inefficient and tedious to program for simple commands with small amounts of data. A better method was needed. We decided to write the code necessary to efficiently use the internet for connected embedded devices with the following goals. First, we wanted to minimize complexity. As soon as a device obtains an IP address, it should be usable. Smart devices should simplify the experience, not complicate it. Next, we wanted to leverage the existing security and request response protocol of the internet. We decided that all operations should occur over HTTP port 80 or HTTPS port 443. Third, we wanted to get rid of the text strings. XML, REST, or SMS all require parsing prior to processing. They waste time, eat up bandwidth, and offer no value to machine-based communication. We also found it was important to have the devices uniquely identify themselves on every network transaction. That meant abstracting away the physical means of communication, Wi-Fi, Zigbee, cellular, Ethernet, or anything new. In many instances, especially mobile, the device will connect in different ways. As an example, you might want to upload or respond to important items immediately via cell, but then upload non-essential data using Wi-Fi. Passing commands along with a data payload within a single transaction showed significant performance increase when the method was applied. And our last goal was to make it platform agnostic. We decided to write all code in pure ANSI C so it could be recompiled for just about any available platform. We both had jobs, so after a couple of years and many program, validate, and debug cycles, we finalized what we call Andromeda. It's an embedded web services platform, and it runs as symbiotic user space applications, forming a client parser model that embeds a binary services layer within the standard HTTP protocol. It exposes itself through a user framework where services written in any language are assigned a name so that you can call them using standard system calls, and a number, which is used by the communication protocol to access the service on a remote device using the standard common gateway interface, or CGI bin, that is provided by a server package such as Apache. In Andromeda, we included a set of commonly used services like send or get a file, or add or delete a database entry. Now, before I get into how we built an intelligent network for the Los Angeles MTA, I want to introduce a couple of terms that may not be familiar to all of you, but they are starting to creep into the IoT vocabulary. And I also want to present the main groups working to standardize IoT protocols. First is network-aware device. It is the ability of a device to recognize the network it is on, as well as all other devices that are on the same network, such that they can all communicate with each other without having to go through a central server. Now, if this sounds a little strange, just think of it as a dynamic name service, but without the overhead of a DNS server. It is accomplished by having a unique device identifier attached to all network transactions. But bear in mind that at least one fixed IP address must exist on the network to serve as a home. And don't confuse an internet-enabled device, that is one that only has connection hardware and runs an OS capable of a network stack, with a network-aware device. Then there are context-aware devices. They are devices that have the ability to know the capabilities of all other devices on the network, such that they can share resources and accomplish the defined tasks of the network. Having context awareness can effectively change the architecture of the internet from being data-centric to a more service-oriented architecture. Devices should be able to run their services and return their data to any other device that requests it. Now, I don't want to minimize the really cool products that are showing up in the IoT space, but the great promise of the Internet of Things isn't that you can open your garage door or set your thermostat from your cell phone. It is that many diverse devices will be able to combine to make life easier or a process more efficient. Your morning alarm will go off earlier because of traffic conditions. The coffee pot will know it's been prepared and start up. The garage door will open when you enter and close when your car is safely out. The lights and coffee pot will shut off as you drive away. The house will know it's empty, so the thermostat will go to your away temperature, and the alarm and monitoring system will engage. All this and much more occurring without human intervention. So when will we start seeing all this magic? The big players have already begun their battles over standards. There are 4 main groups all competing, and in some cases cooperating, to define the language and protocols of the Internet of Things. Probably the best known is the Internet Protocol for Smart Objects. It was formed originally by ARM, Ericsson, Atmel, and Google. In addition to that, there is the Open Interconnect Consortium, which was formed by Intel, Atmel, Samsung, and Broadcom. And then there's the Industrial Internet Consortium, which is composed of Intel, IBM, Cisco, AT&T, and Microsoft. And finally, there is All-Seen, which was started by Qualcomm, Cisco, and Microsoft. How can this not get messy? What I see is that the hardware and platform makers are putting chips in place to support whatever software their particular group comes up with. We're probably going to see an IoT version of the VHS versus Betamax battle for dominance, and that it will be years before a clear direction is obvious. As it stands right now, their focus is on hardware and low-level operations, rather than a comprehensive Internet of Things architecture solution. The good news is that due to consumer demand for high-end portable devices, low-cost Internet-enabled platforms are readily available. This, coupled with the maturity of open-source Linux and Android, allows engineers to build useful IoT networks today that will have the ability to leverage any useful future developments via remote software updates. So enough with the preliminaries. Now let's talk about the issues and how they were resolved in a real-world case where all this and more combined to make a useful, intelligent network for public transportation. It all started with an unsolicited proposal to demonstrate our technology to the Los Angeles Metropolitan Transit Authority, and surprisingly, we got a response. We had our first meeting in August of 2012, where we discussed our capabilities and their requirements. They gave us a list of 6 items that they wanted to evaluate. First, they wanted to track the vehicle in real time and display its GPS location on a city street map. They wanted us to maintain the location history and be able to display where the bus was at any point in time. We had to read the engine control unit via the onboard diagnostics port and record engine health data, and also send an SMS message if any parameters were out of tolerance. We also had to read a passenger counter and record the number of passengers either alighting or egressing and maintain a total passenger count. They wanted us to monitor door state and record idle time, that is, when the doors are closed and the bus is not moving, and then display the idle time as a percentage of the total operating time. And finally, they wanted the ability to add new features remotely. When they asked how long it would take, we said 4 months. Then they asked about the cost, and we said free. Now I think that's what cinched the deal. but was later told that that's what happens when you send an engineer to make a business deal. We arranged to meet a week later with their engineer and tour the bus we were going to interface to. Because it was an in-service vehicle, we were given only 1 day and a wiring diagram to find our attachment points. What their engineer pointed out to us was that the bus had front and rear digital signage with an RS-232 interface. There was a fare box, which also had a serial interface. We found the onboard diagnostic connector for the engine, transmission, and chassis data network, and their engineer confirmed that the protocol was based on the J1939 CAN standard used for heavy vehicles. There was a systems control network based on RS-485 for control of the lights, the doors, and the driver information displays and controls. There was a two-way radio communication system. And their engineer pointed out the integrated passenger counter, which had an RS-485 interface. The bus also had 6 onboard security cameras feeding an onboard DVR, and an onboard video entertainment system that displayed the vehicle location and a variety of local advertising. What we also found and didn't expect was a desktop-sized computer running a proprietary system that used the city's RF band to basically do the same thing that we were going to demonstrate. It was then we realized that this was going to be a compare and contrast exercise, but the die had been cast and we couldn't ignore the downstream opportunities. The hardware selection was reasonably straightforward. Now I want to give a shout out to a few companies, both for their support in this project, and if they hear where they were discovered at an RTECC event, maybe they'll add their support. For the platform processor, the BeagleBoard XM was a no-brainer. We had already used it in other projects and knew it had sufficient power to handle the demonstration. Before deciding on a modem, we drove around LA with borrowed cell phones enabled by different carriers and monitored the signal strength. This led us to a module from Janus Communications. They offer a range of modems that have been pre-approved by different carriers. We selected an open-frame 3G unit that had integrated GPS and was enabled by Verizon. The CAN interface was the most difficult to source. We had neither the time nor budget to write a CAN software stack for detecting and decoding the protocol, and off-the-shelf sources were both expensive and unavailable for ARM architecture. Thankfully, we found a company named Total Phase, who offers a range of instrument-grade serial bus analysis tools in compact, easy-to-use packages. Their products can both read and or write data on a serial bus, such as CAN, USB, or I2C. And they're supported by full GUI-based software as well as C++ library binaries. When we first implemented the supplied binaries, we found them to be compiled for an x86 platform. A call to their customer service resolved the issue. We sent them a BeagleBoard with a GCC toolchain, and they recompiled their library natively on the ARM platform of our choice, then provided us with a download the next day. For the passenger counter, we selected a RS-485 to USB module from FTDI. My years of experience has taught me the last place you want to skimp is on power supply. We selected a medical-grade DC to DC converter from Recom Power to supply the juice. We also decided that a small battery was needed to supply the power for a final data upload when the ignition is shut off. We mounted everything on a perf board and housed it in an industrial enclosure. If you want to see what the finished prototype looked like, it's at the Galixsys table here at the show. The controlling software is also reasonably straightforward. At the system level, we used the Linux kernel and Angstrom distribution that came as a download for the BeagleBoard at the time. Of course, we had to apply some UDEV rules to ensure a consistent boot enumeration for our USB and serial port usage. The modem connection and receipt of an IP address from the carrier is accomplished through a point-to-point options file and a simple chat script. Other methods for connecting to the internet via Ethernet, Wi-Fi, or Bluetooth are well documented in books, online, or by device manufacturers. We added some simple C code loops running as background threads that gathered the CAN, GPS, and passenger count data, and maintained the current data in shared memory files. Then everything was wrapped in about 700 lines of shell script that launched the processes, ensured everything was running correctly, and uploaded a data packet every 6 seconds. This shell script launched automatically after boot up. Uploading every 6 seconds was an arbitrary choice. The data packet was just a row of values that got added to the database. It could have run as much as 10 times faster, but in a mobile, cell-connected scenario, the rate and amount of data uploaded is a balance between the essential needs of the system and the cost of data charged by the provider. Now, where did the data packet go and how was it presented? Well, we leased a server from a company called SingleHop, then installed a MySQL database, OpenLayers mapping, digraph charting, open source packages, as well as our Galixsys Andromeda communication binaries. We registered a domain name with GoDaddy, and that filled the requirements for the demonstration. At that point, a single Galixsys system call uploaded the data packet and stored it in the associated fields of the database. We then created a simple website on the server that allowed specific users to log in with a password. The website also allowed users to select a bus to view and provided access to real-time or historical pages of location mapping, speed over ground, passenger count, or engine health data. Over and under limits were selected for each appropriate data set, and an SMS text message would be sent if an identified number if the values were exceeded. An automatic software update feature was added, and after a week of field trials in my car using data simulators, the system was delivered and installed on a bus with just a couple of Y cables to tap into the CAN and RS-485 data streams and 4 discrete connections for the door positions and power. The bus was returned to service within a few hours in January of 2013, fulfilling our 4-month deadline. The real-world evaluation continued for 6 months, while more users were added to the website and additional engine parameters remotely added to the monitored data. In this slide, you can see the output of the mapping and charting programs we used. OpenLayers mapping had a nice feature where you could click on a spot and a small text box would open up. We used that to show the data collected at that point. The digraph charting interfaced easily with the MySQL database and also let us shade the allowed tolerance area. I can best sum up the success of the evaluation by a comment made by the general manager of the division we were working with. He said, we've spent 6 years and millions of dollars developing a system, and you guys have made it obsolete in 4 months just to show us your technology. Now, to summarize this presentation, first and foremost, don't let engineering set your pricing strategy. No, really. We also talked about network and context awareness in devices. You should abstract away the method of connection so a device can be identified regardless of how it gets its IP address. Try carrying a device identifier with every network transaction. Now, while the public vehicle monitoring example in this presentation was not a very good example of context awareness, the communication between the bus and the remote server were run as binary over HTTP services, and as such, the exchanges occurred much faster than if traditional methods were employed. If you need fast responses among your devices, get rid of the text and the associated parsing overhead. Google reports that a binary over HTTP method is anywhere from 20 to 100 times faster than using traditional XML. See what they say about protocol buffers. Follow what the standards committees are talking about. You don't want to go out on a limb in the wrong direction. Using open source hardware and software, especially to get a project off the ground, can result in substantial savings. As you saw on a previous slide, there are numerous opportunities for connected devices on public transportation. Similar opportunities also exist on light rail and on most vehicles for that matter. Should the video system on the bus be network-based and have facial recognition? Should the onboard advertising change language or run more expensive targeted ads based on the GPS location? Do the police need to remotely kill the ignition? Maybe they could use some accelerometers and gyro sensors to monitor driver reactions or for crash analysis. The simple point is that opportunities for connected devices will continue to grow for the foreseeable future. There are vast stores of sensors. Many manufacturers have products to contribute to an IoT infrastructure. But who's taking the mile-high view? Hardware and software engineers are connecting really cool devices on an individual basis, but how are these devices going to connect to each other, and how will they communicate? What the Internet of Things really means is having network and context-aware devices running under a service-oriented architecture and requiring no human intervention. This is being discussed in academic circles and is available from Galixsys now, and we believe that this will fulfill the promise of a real Internet of Things. Thank you for listening.